This lesson is over solving polynomials of higher degree with factoring. Well, what exactly does it mean to solve polynomials of higher degree with factoring? That sounds kind of mathy. So first we look at the word polynomials. What does that mean? Well, binomials means it has two terms. Trinomials mean it has three terms. Well, poly just means many. So when you see polynomials, it means it's going to have many terms. Next it says of higher degree. Degree is simply a fancy word for an exponent. So we're going to be looking at expressions that have many terms with higher exponents than what we're used to. So let's look at the following. We have 3x cubed plus x squared minus 12x minus 4 equals 0. Well, is this linear? Remember, linear means you only see an x raised to no power. Nope, not linear. Is this quadratic? Again, a reminder, quadratic means x squared is the highest exponent. Is this quadratic? No. So what do? Well, this is called a polynomial of higher degree. Notice it had a higher exponent than 2. So the approach to solve these is a little bit different. Since it's not linear, we cannot isolate the x. But let's try to use the same methods as a quadratic and see if it works. Recall, to solve quadratics we had a few steps. Our first step was to make sure the equation was equal to 0. Once it was equal to 0, we then had to check the order. It needed to be in descending order according to the exponents. From there, we factored according to the number of terms. And then once it was factored, we set each linear piece equal to 0 and solved. So let's look back at that problem. Again, it was 3x cubed plus x squared minus 12x minus 4 equals 0. Well, look at this. Does it equal 0? Yes. Is it in the correct order? Yes. Now, we need to factor according to the number of terms. And the part we're looking at is the left side of the equation. So we are going to factor this on the side of our paper. Since we have 4 terms, remember, we tend to do factor by grouping. If we look at the first 2 terms, 3x cubed plus x squared, we notice they have an x squared in common, which leaves you with 3x plus 1. The last 2 terms, negative 12x minus 4, have a negative 4 in common. So if we factor out a negative 4, that leaves us with 3x plus 1. Since we factored the first 2 terms and the last 2 terms, now the GCF is visible. Both pieces have a 3x plus 1. And if we factor out a 3x plus 1, that leaves us with x squared minus 4. So we have factored it, but now we want to make sure it's completely factored. So we look at the first parenthesis set. Is that linear? Yes, because we only see an x. Is the next parenthesis set linear? No, that one is quadratic because we have x squared, which means we need to see if it can factor again. So only looking at the quadratic parenthesis set, we look at how many terms we have. Since we have 2 terms, we want to see if it can factor according to a pattern, specifically difference of squares. Is x squared a perfect square? Yes. Is 4 a perfect square? Yes. Is there a minus sign? Yes, which means this does factor into two binomials. This will factor into x minus 2 and x plus 2. But we can't leave behind the other factor. We still have 3x plus 1. Now we check all those parenthesis sets. Are they all linear? Yes, which means we have completely factored, so we can take our factors back to the equation. We now have 3x plus 1 times x minus 2 times x plus 2 equals 0. So we interpret this as some number times some number times some number equals 0. So one of those values must be 0 in disguise. So let's solve. We take the first piece, 3x plus 1, and we set it equal to 0. Now we solve for x. We would subtract 1 on both sides, divide the left side and the right side by 3, leaving us with x equals negative 1/3. The next piece is x minus 2, and we set it equal to 0. Again, we want to solve for x, so we add 2 to both sides, and we find x equals positive 2. The last piece is x plus 2, and we must set that equal to 0. And again, we solve for x by subtracting 2 on both sides. And these are your solutions. X equals negative 1/3, positive 2, and negative 2. Example 1, we have x to the 4th minus 5x squared plus 4. So again, we're being asked to solve, so we want to see, does our equation equal 0? Yes. Are the terms in the correct order? Yes. So now we look for the number of terms that we have. Since we have x to the 4th minus 5x squared plus 4, that means we only have 3 terms. So we are going to factor on the side of our paper. We're only focused on those 3 terms. Now, since it is 3 terms, we must factor using the AC method, which means to multiply your leading coefficient times your constant or plain number. In this example, that means we have a 1 times a positive 4, which gives us a positive 4. From here, we create a list of multiples. 1 times what, 2 times what, and so on. Well, for us, that gives us 1 times 4 and 2 times 2 as the only possibilities. Now that our list is complete, we go back and look at the sign. Because it's a positive 4, that's giving us a clue that we must add the values. They have to add to equal the middle term, which in this case is a negative 5. Well, there is a possibility when we're looking at 1 and 4. Now, to add, they must have the same signs, whether the 1 and 4 are both positive or the 1 and 4 are both negative. In which case would we get a negative 5? Well, that would be the negative case. So we expand the middle term. Instead of negative 5x squared, we replace it with negative x squared minus 4x squared. So we went from 3 terms to now 4 terms. And the reason for doing that is so that now we can do factor by grouping. Your first 2 terms have x to the 4th minus x squared. Well, their GCF is x squared. And if you factor out an x squared, it leaves you with x squared minus 1. Now we look at the last 2 terms. Negative 4x squared plus 4. In their GCF, it's not 4, but negative 4, which leaves you with x squared minus 1. Since we factored the first 2 and the last 2, now we look at the problem again. Do we have a common factor? And it turns out we do. Notice x squared minus 1 appears in both places, so that is our GCF. And when we factor that out, it leaves us with x squared minus 4. So we have factored it, but we want to make sure it's factored completely. So if we look at the first parenthesis set of x squared minus 1, is that linear? No, it's actually quadratic, which means we need to see if it can factor again. Since it has two terms, we want to see if it falls into the pattern of difference of squares. Is x squared a perfect square? Yes. Is 1 a perfect square? Yes. Is there a minus sign? Yes. So this does satisfy the difference of squares, which means it will factor into x plus 1 and x minus 1. Now we look at the next parenthesis set. Is that linear? No. That too happens to be quadratic. So again, we need to see if it can factor. Because it has two terms, we look to see if it follows difference of squares. And notice it does. This will too factor into x plus 2 and x minus 2. Now we look at each of those parentheses and make sure that each one is linear. And they are. So we can now bring these back to the original equation. And so we now have x plus 1 times x minus 1 times x plus 2 times x minus 2 all equals 0. And so since we have some number times some number times some number times some number equals 0, well, that means we need to set each individual piece equal to 0 and solve. The first piece, x plus 1, we set equal to 0, and we solve for x by subtracting 1 on both sides, and we find x equals negative 1. The next piece, x minus 1, we set equal to 0. We solve for x by adding 1 to both sides. We find x equals 1. The next piece is x plus 2. We set it equal to 0 and solve for x by subtracting 2 on both sides, giving us x equals negative 2. And then the last piece, x minus 2, we set equal to 0, and we solve for x by adding 2 on both sides, and we get x equals positive 2. And so, these are your solutions.